In this video, we are going to take a look at functions. What is a function? How do we represent a function with notation? And then also we're going to look at recalling what domain and range is. So in order for an equation or a graph to be an example of a function is just simply a relation. Now a relation can be anything we want, any set of points, any kind of graph, where no two different points have the same x-coordinate point. So for a specific x value, there can be only one y. So for any input, there can be at most one output, is another way to think about it. Again, relation being anything, and then more strict than a relation would be this function. So just a couple of quick examples to show the difference between the two. If I had the equation y equals x plus 3, if I ask you if an equation is a relation, you can take a look at it. By testing it, you can make a table and determine if you have two different y values for a specific x. So real quick, y-intercept is 3, up 1 over 1, so something like this. So if I were to make a table for this, there wouldn't be any two pairs of different y values for a specific x. So this relation is a function. The second example is x equals y squared. So if you remember x equals y squared, again, you could make a table. If I was going to make a table, I'd specifically pick y values if I forgot what this looks like. Otherwise, if you remember what this looks like, it's just a sideways parabola with the origin at 0, 0. And now for this one, this is an example of just a relation, not a function. Because if I look at the value at positive 1, positive 1 up here, sorry. If I put 1 in up here for y, I square that and I get positive 1 out. Also, if I go down here at negative 1, I put negative 1 in for y I squared, I also get positive 1 out for x. So there are two distinct coordinate points when my x value is 1. I substituted in y to make it a little bit easier, but at 1, my y value is 1, and when x is 1, I have a y value of negative 1. Because it is the same x, and it has two different y's, this is an example of a non-function. And we can use what's called a vertical line test to check it quickly to see if it works. I can draw an infinite number of vertical lines through my relation, and if it crosses my graph at two different spots, it's not a function. It's just an example of a relation. So this case here, I specifically made it go through those two coordinate points. So that's another example as to why this is not a function. It's just a relation. Here are 4 different examples of relations, and now we need to determine whether or not they're functions. So if I use my vertical line test and draw in those are vertical lines, an infinite number of vertical lines, it only crosses that red graph at one spot. So this first one is a function. This one here, draw an infinite number of vertical lines. Right here there's a hole, but that's no big deal. Even though there's a hole there, it doesn't cross my graph more than once, which means this is also an example of a function. And the one on the bottom left, function, 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 non-function. As soon as it crossed at more than one spot, this is a non-function. We can just call that a relation. And the last one, all single points. Now, keep in mind that open circle means it doesn't cross there. It crosses later. Perfectly acceptable. This would be an example of a function. However, if I had that circle there filled in, this line on the end here fails the vertical line test. It crosses at two different spots. When it was the open circle, it was fine, but as soon as it's a closed circle, it wasn't. So when we have a function, we can use what's called function notation to represent it. So a traditional equation in the past would have been y equals 2x plus 3. And you learned in Algebra 2 that we can rewrite this as f of x equals 2x, excuse me, plus 3. And just a new notation that you're going to see now, these are perfectly acceptable. There's nothing wrong with using these. But if you see this next notation, you need to make sure that you're comfortable if you see it. You don't always have to use it, but you need to understand how it works. And it's written as follows. F colon x with this little arrow, and then the function 2x plus 3. What this represents is this f here means function f. The colon means such that, and then this whole phrase means x, because it's starting with x here, is converted into 2x plus 3. So it takes your x value and it makes it into 2x plus 3. So that's the notation that you are going to be seeing, because what's realistically going to happen, what that really means, is it's going to take your function f such that x is converted into f of x, because f of x represents what your function is, 2x plus 3. So again, that's just what the notation is, so that you feel okay when you see it. If you see this function notation and you want to convert it up into here, that's perfectly acceptable. So this would be the type of example that you could see this with. So if f such that x maps onto x plus 3 over x, find the value of f of 3 and f of 0. So understanding just with notation that this initial notation here is exactly the same thing as f of x equals x plus 3 over x. And as soon as you understand that, it's plugging it in just like you normally would. So it says f of 3. 3 is that x value. So you plug 3 in for x. Simplify. F of 3 is 4. Plug in 0. I'm going to instantly see that when I plug in 0, I'm done. Please remember, that's 3 divided by 0, which is undefined. We will talk more about undefined numbers and scenarios, but just understand that that is an undefined value for x. The last part that we're going to look at with our functions is domain and range. So remembering back to the work that you did in Algebra 2, remember that domain is just your set of all possible x values, and your range is set of possible y values. Keeping in mind x's are those input values, those independent values. Y's are your output values, which are your dependent variables. So I can go through and take a look at specific types of graphs, determine what domain and range is. Again, this is just going to be one more slight difference in notation so that you can write the notation like you've always written it or use this specific type. So in these two examples, we're going to find the specific domain and range of each. So we'll start with the one on the left, a little bit more traditional. The one on the right is going to be a little bit different. So the one on the left, if I'm going to do my domain, a way to represent your domain is with this set bar, the x, and then this line. What this means is the set of all x such that. That's what those three things mean. The set of all x such that. And then I need to look at what my x values are. Well, the lowest x value that I possibly have is -1, and then it shoots off to infinity. So therefore, x has to be greater, it's closed, so equal to -1. And that's your domain for this problem. You close it with that set bar. For your range, looking at what your y values are, so find the lowest, find the highest if there is one. The lowest value is -3. Very similar notation. It's the set of all y this time. That bar such that y is greater than or equal to -3. Close your set, and you have your domain and range for the first example. Take a moment, pause it, see if you can write down this one. Even though it's a little different, see if you can start with your notation. So for my domain, looking at what my possible x values are. So it's the set of all x such that. So when I look at my x values go from here over, and from here down. So it's a range, it's a set of two different types of numbers. So it's from greater than 1 or less than or equal to negative 1. Now I said greater than 1 because there's an open circle right here at positive 1. So therefore I list both of those sets out. So x has to be less than or equal to negative 2. I think I misspoke. This is negative 2 for your x value, sorry. Or x has to be greater than positive 1. Because again, it has that open circle. For your range, it's a set of all y's such that, this time when I'm looking up and down, I notice that my y values go from negative 1 down and from positive 1 up, but not including it. So that's going to be just a greater than 1 again, not a greater than or equal to. So y has to be less than or equal to its y value, which is negative 1, or y has to be greater than, just greater than, positive 1. It doesn't matter in which order you set those up in. Just make sure you put the or statement in there because you are doing a span from here to here or from here to here. That's where all possible x values for domain, y values for your range are.